All right, so when I ask a question about time complexity, I've got to figure out what I'm talking about. So, here in this particular algorithm, I need to, one, identify an input size. So what is my input size? Well, I have an array of coefficients, right? The array it has n plus 1 coefficients. So my input size is, let's just call my input size n, right? So n is related to the number of coefficients. It's one less than the number of coefficients. Number two, what's my basic operation? Well, a good idea, anytime you have something like this with nested for loops, is to consider the thing that happens on the inside of the innermost for loop as your basic operation. And so this isn't quite a foolproof approach, and we'll see some examples where it's a little more complicated than that. But this is a good place to start. So here, this multiplication here, we will consider our basic operation. So let's say the multiplication. Multiply in this one. So what we'll literally be asking is how many multiplications are performed by this algorithm when we give it a polynomial of degree n. So literally what we're asking here isn't so much an input size question. It is how many multiplications to evaluate a polynomial of degree n. Okay. So there's how this goes, and so now the question is, what's our expression for the number of multiplications? So what is t of n? Where n is the degree of the polynomial, and t represents the number of multiplications, the number of mults. Well, we have two nested for loops. There are no termination conditions in this algorithm. So if we give this thing an array of size 10 and an x, it'll go through the for loops just the same as if we gave it some other array of size 10 and some other x. Right? There's nothing in here that can cause some kind of premature termination. And so what that means is that we can very easily just write down these for loops in the form of summations. Okay, so what are the summations that do this? Well, here I'll write my t of n has a summation for the outer for loop. So the sum from I equals 1 to n, and that captures the outer for loop. And then it has a summation for the inner for loop. So this is going to be j equals 1 to I. And how many multiplications happen on the inside of each of the inner for loop? Well, just one. Just one multiplication happens. Okay, so now let's just focus on this. Right now we have some math, so we can evaluate the math. All right, so this is our t of n. Right, it's a function of n. N enters here, so there's the n in it, and it has summations, and we have all the formulas and comfort that we need for evaluating this. So always with these, you start on the inside, right? And I'll evaluate this one in complete detail. In the future, there's some steps we can skip, but for this one, we'll just be complete. So the outer sum goes like this, and I'll just leave it as is. I'm not gonna modify it at all. And then I'll use the formulas, if you will, that I have for computing sums of fixed limits to evaluate the inner sum. And so here, to be very complete, the formula says I'm gonna take where I end up, which is I, subtract from that where I started, which is 1, and then add 1 more in. And this comes out to the very simple expression, just I, right? I minus 1 plus 1 is I. And what we're left with is a simple arithmetic series. Okay, so this is what we could have kind of seen coming if we had stepped through the actual polynomial evaluation process and figured it out ahead of time. So what does this mean? I mean, this means the simple fact that we have 1/2 n times n plus 1 multiplications. And if you look at this, you see there's an n squared term in this polynomial. And we could write that out in extreme detail, or we could just notice, hey, this is an n squared algorithm, right? And the proof here is just the following, that we have the expression is actually just 1/2 n squared plus 1/2 n, which, because it's a polynomial of degree 2, we know that this is an n squared algorithm. So if I give this thing a polynomial of degree n, it'll take order n squared multiplications to evaluate the polynomial. All right. So this is a result, right? We just derived the complexity, the time complexity of this algorithm, and it remains to ask, could we have done better, right? Was this algorithm the best that we could do? What we did is we said, hey, here's the mathematical expression. Let's just walk through it and kind of brute force evaluate it and see what we get. And we ended up with an n squared algorithm. But we have no context for n squared unless we can identify how good it is, right? N squared can be fast for certain kinds of algorithms, and it can be slow for certain kinds of algorithms. So let's think about what we could have done better.